The problem is this: a spherical shell with outer radius B surrounds a charge-free cavity of radius A, which is less than B. So we're looking at this. Here's A, here's B. There's no charge density inside radius A. And in between these two, there is a volume charge density, which is equal to minus rho V naught over R squared inside. And we are asked to find the electric flux density in all regions. So, first of all, what are the regions? The regions that we have to deal with are R less than A, where there's no charge density, R between A and B, where the charge density varies with position, like that, and R greater than B, where again there is no volume charge density. Let's go through the steps of how to solve this problem. First of all, what law or equation or tool can we apply? Now, we sort of gave it away with what I said at the very beginning of this example. This is a Gauss's law problem. But the way that we can tell that is that this is a problem with really nice symmetry. We have a spherical geometry here. Nothing depends on angle. Everything only depends on the radius. That's a really nice spherical geometry. It's very symmetric. If we rotated it about the origin in any way, it wouldn't matter. It would still be the same problem. So, we're going to use Gauss's law. Step 2 then is, how do we apply Gauss's law? We're going to have to choose a Gaussian surface. And the things that make a good Gaussian surface are that we need the electric flux density should be parallel to the surface normal vector, or the electric flux density should be perpendicular to the surface normal vector, or the electric flux density should be equal to 0. One of these things has to be true. Everywhere on our Gaussian surface. So let's look at the symmetry of the problem. What is the direction of the electric flux density? Go back up. Look at the symmetry of this problem. Well, it's a very spherical problem. Nothing seems to depend on angle. We have this charge density here. If I pick some point out here and I think about what components that charge density might have, it's definitely going to have some component that's pointing either towards or away from the sphere, depending on the sign of the charge density. Here it's negative, so I guess it would be pointing inward. Right, so it's going to have some component that's going to be pointing that way. But is it going to have any angular components this way or this way? Well, some charge element over here on the sphere would contribute a field component that has some component that points that way. And I could choose, but I could choose some other charge component that is symmetrically located on the sphere over here that would have an equal and opposite component in the other direction, so they would cancel out. At any observation point, I can choose two opposing locations on the sphere to cancel out any non-radial components. So the spherical symmetry cancels non-R components of D. So that means that it's R-directed, which means for this, I need to choose a Gaussian surface where its surface normal vector is R hat, or it's R hat directed at least. Or I need to choose a Gaussian surface whose surface normal is perpendicular to that, or I need to choose a Gaussian surface where the direction of D, or where the magnitude of D is 0. The easiest thing to do here is to choose a sphere. So a sphere of arbitrary radius r satisfies all these conditions because everywhere that our electric flux density exists, it's r-directed, and so is the surface normal vector. So that makes our life easy. So now our geometry looks like this. Here's our outer shell with radius b. Here's our inner charge-free region with radius a. I have my Gaussian surface at some location in between these two, which is a sphere of radius r, some variable arbitrary value r. We don't know what it is, and we are going to allow it to vary to find out what the value is of that electric flux density in all three regions. So let's remember what exactly is Gauss's law. It is that the charge enclosed by the Gaussian surface is equal to the flux integral of the electric flux density. So we're going to end up doing two integrals in this problem. We're going to do one on the left-hand side. We're going to do a volume integral to find the total charge. And on the right-hand side, we're going to do this flux integral. The flux integral is really simple, so let's do that one first. We will start by assuming that D has the form r hat times D, which is a function of r. And when we're doing a surface of a sphere surface integral, we know that the differential surface element ds is going to be r hat for one, and then it's going to be r squared sine theta d theta d phi. If you don't remember why it's like that, think back to the day in class where we did all those diagrams and pictures in the coordinate systems. I think that was chapter 3. So, substituting these two facts in, and the bounds of the surface of the sphere are going to be theta between 0 and pi and phi between 0 and 2 pi. So substituting all of these things in, I end up with, move over here so I got some space, integral from 0 to pi, 0 to 2 pi of d of r, this is the magnitude of the electric flux density, r hat dot r hat r squared sine theta d phi. This r hat dot r hat evaluates to 1. D of r stays the same because we are not integrating with respect to r. So that can actually move out to the front of the integral. And then what's left is d of r times r squared times the integral 0 to pi, 0 to 2 pi of sine theta d phi. The integral d phi just gives us another factor of 2 pi. So we're left with the theta integral to evaluate. And the integral of sine theta is, I always forget if it's positive cosine or negative cosine. So the way that I figure it out is I draw a graph of sine theta, and I remember that the derivative of sine theta is positive here, and this is a positive cosine. So this is so since I've eliminated positive cosine, that means that the antiderivative of sine theta d theta would have to be minus cosine. All right. With that in mind, I have to evaluate that little bit of the integral that's left over. So I got 2 pi r squared, amplitude of my electric flux density, times cosine minus cosine theta, evaluated from 0 to pi. When I evaluate that, I'm going to get minus 1 minus 1, because this minus sign gets applied to both of them, and I have to subtract the two bounds, and then this minus sign is that minus sign, but cosine of 0 is positive 1 and cosine of pi is negative 1. So the answer there is 2. So that whole flux integral works out to 4 pi r squared d of r. And remember that this is the amplitude of d.